Hello students, welcome to this session on solution to review assignment 2. Question 1, suppose x1, x2 up to xn are IID random variables with an unknown mean theta and theta hat, this is the estimator, is given by 2 by n into n plus 1 into summation I xi, I going from 1 to n. Find E of theta hat, variance of theta hat and MSE of theta hat. Is theta hat unbiased and consistent? Is theta hat an MVUE? Solution. So, we are given that theta hat is equal to 2 by n into n plus 1 into summation I xi, I going from 1 to n. Therefore, E of theta hat will be equal to 2 by n into n plus 1 into, now expectation of this sum is same as the sum of the expectation. So, that way into summation I going from 1 to n, I is a constant into E of xi. So, that way now unknown mean is theta, therefore, this will be equal to 2 by n into n plus 1 into theta summation I going from 1 to n into theta. Theta is common everywhere. So, this summation is now given by n into n plus 1 by 2. So, that way 2 by n into n plus 1 into n plus 1 by 2 into theta. So, that this will be equal to theta. Therefore, theta hat is unbiased. We can find out the variance of theta hat, because it is an unbiased estimator. So, variance simply we can find out that is equal to 2 by n into n plus 1 whole square, because this is a constant. If we take the variance, this constant will be square into summation I again a constant. So, it will be I square into variance of xi, I going from 1 to n, and all the cross terms will become 0 because xi's are independent. So, that way this will be equal to 2 by n into n plus 1 whole square. Now, variance of xi, this is IID, therefore, variance of xi is same for all xi's. So, we can take it out. So, this will be sigma square suppose. Then this will be summation I going from 1 to n, summation of I square I going from 1 to n, and this is equal to, so 2 by n into n plus 1 whole square sigma square, and this is n into n plus 1 into twice n plus 1 divided by 6. So, this, if we simplify this expression, we will get this is equal to, so 2/3 will be here, 2/3 of then here n is there, 1 n will get cancelled. So, n into n plus 1 here, and this part will be there, twice n plus 1 here, and then this sigma square. So, this is the variance of theta hat. So, we have found out the E of theta, variance of theta. We have found out E of theta hat and variance of theta hat. Now, we will see MSC of theta hat. Now, MSC of theta hat. So, we know MSC is equal to variance var of theta hat plus bias of theta hat square, but since E of theta hat is equal to theta, bias is 0. So, that way this will be simply this expression only, 2 by 3 twice n plus 1 divided by n into n plus 1 into sigma square. So, that theta hat is unbiased. Is theta hat unbiased and consistent? So, next question is whether theta hat is consistent. So, since it is an unbiased estimator, now we have variances. So, to prove consistency, we have variance of theta hat is equal to, that is 2/3 of twice n plus 1 divided by n into n plus 1 into sigma square. So, for to take, because it is an unbiased estimator, to check whether it is consistent or not, we have to see limit variance of theta hat as n tends to infinity. So, we see that there here n is there. So, this part as n tends to infinity, it will become 0. So, we see that limit of variance of theta hat as n tends to infinity is equal to 0. Therefore, theta hat is a consistent estimator. Next question is theta hat an MVUE? So, we have variance of theta hat is equal to we know that there is another estimator, suppose sample mean, that is theta bar is equal to 1 by n into summation xi, I going from 1 to n. And in this case, variance of theta bar, this will be equal to, if another estimator theta bar is there, this variance of theta bar will be equal to, we can show that this is sigma square by n. Now, this quantity is less than this. So, variance of theta bar is less than variance of theta hat. We can, because here this is this expression is always larger than 1 by n. Of course, for n is equal to 1, both will be same, but otherwise this variance of theta hat will be greater than variance of theta bar, except for for n is equal to 1. N is equal to 1, in that case this will be also sigma square, this will be also sigma square. So, therefore, there exists an estimator theta bar with variance lower than the variance of this estimator. Therefore, this theta hat is not an MVUE. It is not an minimum variance unbiased estimator. It is unbiased estimator, but it does not have the minimum variance. Next question, suppose x1, x2 up to xn are IID and xi distributed as Bernoulli distributed, Bernoulli random variable. This is the symbol for Bernoulli random variable. This is binomial with parameter 1 and theta. Find the Fisher information statistic I theta. Find the CRLB for the variance of an unbiased estimator theta hat. Examine if the CRLB is reached by the variance of theta hat is equal to this summation xi, I going from 1 to n divided by n. So, this is the estimator whether the variance of this estimator satisfy CRLB, Cramér-Rao lower bound. Now, in this case, there are n random variables are there. Therefore, the joint PMF probability mass function, that is also likelihood function, that is equal to P of, if I write in vector notation, x theta. So, that is equal to P of x1, x2 up to xn, and as a function of theta, and this is equal to, now because it is IID, independent and identically distributed. So, it will be product I is equal to 1 to n, and each random variable is Bernoulli distributed. Therefore, this will be theta to the power xi, theta to the power xi, and 1 minus theta to the power 1 minus xi. So, this is the probability, joint probability mass function. So, we can take the logarithm L of x theta, this is a vector x theta, that is equal to log of P of x theta, and if I take the logarithm, this will be summation log of theta to the power xi 1 minus theta to the power 1 minus xi summation I going from 1 to n, and this I can write as whole summation. This is I going from 1 to n, this is xi into log of theta, and plus, because it is logarithm, 1 minus xi into log of 1 minus theta, and this I can write as log of theta into summation I is equal to 1 to n xi plus log of 1 minus theta into n minus summation xi I going from 1 to n. Now, we have to take the first partial derivative del L del theta. Therefore, del L del theta, that will be equal to 1 by theta here, then summation xi I is equal to 1 to n, plus, now this is log of 1 by theta, its derivative will be 1 by 1 minus theta, and then because it is minus is there, so there will be minus 1 will be there, minus 1 by 1 minus theta into this term n minus summation xi. Now we can find out information statistic by finding either E of del L del theta whole square, or we can go to the second order partial derivative E of del to L del theta square. So, we can carry out the second order partial derivative del to L del theta square will be equal to, this will be minus 1 by theta square into summation xi, I going from 1 to n, and this one will be minus is there, then so minus minus will be plus, again minus will come. So, that way it will be minus 1 by 1 minus theta whole square into summation n minus summation xi. This is I going from 1 to n. So, we have to take the expected value of this, because information I theta is equal to minus of expectation of del to L del theta square. So, and therefore, I theta is equal to, that is equal to minus of E of del to L del theta square. So, now if I take the expectation here, E of xi is equal to theta, therefore, n theta will be there and 1 theta will get cancelled. So, that way it will be, first term will be n by theta square, and similarly here this will be n theta, n minus n theta. So, that way 1 minus theta term will get cancelled. So, here we will simply have n divided by 1 minus theta, this one is n by theta. So, that way this is the expression, and we have also a minus term. So, minus of entire thing. So, that will be equal to, if I carry out the simplification, theta into 1 minus theta, and this one will be, so 1 minus theta plus theta. So, that way it will be simply n. So, therefore, I theta is equal to n divided by theta into 1 minus theta. So, this is I theta. Second part B is, this is part A, this is A. Part B is, we have to find out CRLB. CRLB for variance of theta hat, unbiased estimator theta hat will be equal to, because 1 by I theta, that is equal to theta into 1 minus theta divided by n. So, to see if CRLB is reached, so we will find out that del L del theta. Del L del theta we have already found out. Let me write down. Del L del theta is equal to, if we simplify, this will be equal to summation xi, I going from 1 to n, minus, this will be theta into n divided by theta into 1 minus theta. That way we can simplify this. And if I take n common, so n into summation xi divided by n, this I is going from 1 to n, minus theta divided by theta into 1 minus theta, and this is equal to n divided by theta into 1 minus theta, and this quantity is our theta hat minus theta. So, therefore, we see that equality condition is satisfied, and this quantity is the I theta into theta hat minus theta. So, del L del theta, therefore, del L del theta is equal to I theta into theta hat minus theta. Therefore, variance of theta hat reaches the CRLB. So, that way we prove this result. Next question is, suppose x1, x2 up to xn are IID and same distribution xi is distributed as Bernoulli with parameter 1 and theta, that is binomial with parameter 1 and theta, that is same as Bernoulli distribution, and Tx is equal to summation xi I going from 1 to n. Tx is equal to summation xi I going from 1 to n. Examine if Tx is a sufficient statistics and if Tx is a complete statistic. Use Tx to find an MVUE for theta. So, in this case, we have Tx is equal to summation xi I going from 1 to n. And likelihood function, we will see the joint PMF here. Already we have find out P of x as a function of theta, that is the joint PMF. So, that is equal to product of I going from 1 to n, because IID and individual distribution is theta to the power xi into 1 minus theta to the power 1 minus xi. So, this I can write as theta to the power summation xi and I going from 1 to n, and similarly 1 minus theta to the power summation 1 minus xi I going from 1 to n. So, that way this will be theta to the power summation xi I going from 1 to n, 1 minus theta to the power, this first term will become n minus summation xi I going from 1 to n. And this I can write this 1 by theta to the power minus summation xi I going from 1 to n, that I can write here. So, that way theta by 1 by theta to the power summation xi I going from 1 to n into 1 minus theta to the power n. So, this is Tx. So, this is equal to theta by 1 minus theta to the power Tx, and then 1 minus theta to the power n, and this is same, we can see that this factorization theorem is satisfied. We can take this as the g of theta Tx into hx. This hx is equal to 1. So, hx is equal to 1 and g of theta Tx is equal to this. So, that way we see that factorization theorem is satisfied, because we know that in the case of factorization theorem, if the joint PMF or joint PDF can be expressed into two factors like this, one simply function of x, another is a function of the parameter and the statistic. So, that way this PMF satisfy this factorization theorem, therefore, Tx is a sufficient statistic, To see whether Tx is complete or not, we have to consider this quantity E of g Tx. So, now Tx is equal to summation xi I going from 1 to n. Since xi's are Bernoulli, Tx will be equal to k going from 0 to up to n. So, that way this will be equal to summation, and Tx is distributed as binomial with parameter n and parameter theta. So, summation I going from 0 to n, this will be g of k into, now this is binomial distribution. So, that way n c k n k, that is the combination n k into theta to the power k into 1 minus theta to the power n minus k. So, this we can write as summation I is equal to 0 to n g k n c k theta by 1 minus theta to the power k, and this 1 minus theta to the power n I can write here 1 minus theta to the power n. Now, we want E of gtx is equal to 0 for all theta, and but this quantity is a polynomial in theta by 1 minus theta to the power k, and this can become 0 only if this gk is 0, only if gk is 0. Why? Because this quantity is a polynomial. So, a polynomial can be 0 if only its coefficient is 0, but this quantity is non-zero. So, gk must be equal to 0, implies that g of tx is equal to 0 with probability 1. So, therefore, Tx is a complete statistic. Tx is a complete statistic, that we have proved. Use Tx to find an MVUE for theta. So, we have to use Tx to find an MVUE for theta. Now, Tx is equal to summation xi. Therefore, any unbiased estimator involving Tx will be the MVUE. So, there is only one unbiased estimator involving this Tx. Therefore, theta hat is equal to 1 by n summation xi I going from 1 to n will be the MVUE. So, according to that Lemon-Cephei theorem, we can have an unique unbiased estimator with minimum variance property, and there is only one unbiased estimator here, that is summation xi I going from 1 to n divided by n. Therefore, this is the MVUE. We will go to question 4. Suppose x1, x2 up to xn are IID, identically independent and identically distributed, and xi is distributed as normal with mean 0 and variance theta. Find theta hat MLE for the unknown parameter theta. Theta is the unknown parameter. We have to find out the ML estimator for theta. Examine if the above theta hat MLE is unbiased and consistent. Another parameter beta is derived from theta by the relation beta is equal to half of theta minus 1. Find beta hat MLE. So, here the joint density function is given by f of x, this is a vector, as a function of the unknown parameter theta is equal to, because it is IID, it is the product of the individual PDF, that way product I going from 1 to n, and its density is 1 by root over 2 pi theta into e to the power minus 1 by 2 theta into xi minus 0, because mean is 0 whole square. Okay. So, this is equal to 1 by root over 2 pi theta to the power n into e to the power minus 1 by 2 theta into summation xi square I going from 1 to n. Now, if I take the log of this expression, that is L of x theta will be equal to, now there is a theta to the power n by 2 is there. So, log of theta to the power n by 2, that will be n by 2 log theta. So, that when n 1 by is there. So, that way n by 2 log of theta, and this term will come as minus 1 by 2 theta summation xi square I going from 1 to n plus some term independent of theta, because we will be taking derivative with respect to theta, independent of theta. Now, we will take the derivatives del L del theta, that will be equal to minus n by 2, this is log theta 1 by theta, that will be, and this will be minus minus will be plus 1 by 2 theta square summation xi square I going from 1 to n, and this term derivative will become 0. Now, for maximum likelihood estimator, del of del theta at theta hat MLE is equal to 0. So, del L del theta at theta hat MLE is equal to 0. Putting theta hat MLE here, so we will get that theta hat MLE is equal to 1 by n summation xi square I going from 1 to n. So, this is the maximum likelihood estimator for theta. Next is examine if the above theta hat MLE is unbiased and consistent. So, E of theta hat MLE, this is the solution to part A. Now, for part B, E of theta hat MLE is equal to 1 by n into summation I going from 1 to n E of xi square. Now, this is a 0 mean, therefore, E of xi square is variance and IID. So, that way and there will be 1 by n into E of xi square is theta. There will be n such term. So, n theta, and that will be equal to theta. Therefore, theta hat MLE is unbiased. So, this is the solution B, and there is also, we know that ML estimator is always consistent. Theta hat ML is always consistent. Therefore, this is true. Theta hat MLE here also it will be consistent. So, this is the solution of part B. Now, in part C, we have another parameter, that is beta is, for part C, beta is equal to half of theta minus 1. Now, question is, what is beta hat MLE? Now, we will use the invariant property of ML estimators, that is beta is a function of theta. Therefore, we know that if we know the theta hat MLE, then we can find out beta hat MLE, because you have to put just theta hat MLE here. Therefore, beta hat MLE will be is equal to half of theta hat MLE, which is given by this theta hat MLE is given by this one. So, theta hat MLE minus 1. So, how do I get it? Using invariant property of ML estimator. So, therefore, beta hat MLE will be given by this. We will go to the next question. Suppose x1, x2 up to xn are IID Gaussian random variables with unknown mean mu. Mu1 hat is equal to half of x1 plus xn, and tx is equal to summation xi I going from 1 to n is a complete sufficient statistic for mu. So, you are given that xi's are IID Gaussian with unknown mean mu, and mu1 hat is an estimator given by half of x1 plus xn, and tx is a complete sufficient statistic for mu, and it is given by this summation xi I going from 1 to n. Examine if mu1 hat is an MVUE. Then part B is find an MVUE for mu in terms of tx, and C is apply appropriate theorems to find E of mu1 hat given tx. So, here mu1 hat is equal to half of x1 plus xn. Therefore, E of mu1 hat will be equal to half of E of x1 plus E of xn. Now, xi's are IID, so all will have the same mean mu. Therefore, this will be half of mu plus mu, that is equal to mu. Therefore, mu1 hat is unbiased. Variance of mu1 hat will be equal to, again these are IID, therefore, this will be 1 by 4 into variance of x1 plus 1 by 4 into variance of xn, because x's are IID independent, therefore, we can write like this, and this will be equal to variance of x1 is equal to, suppose, sigma square, then it will be sigma square by 4 plus sigma square by 4 is equal to sigma square by 2. So, this is the variance of mu1 hat. Now, we know that suppose mu hat is equal to 1 by n summation xi I is equal to 1 to n. Then in this case we know that variance of mu hat is equal to sigma square by n, which is lower than sigma square by 2. Therefore, this mu hat is an estimator which has variance lower than the variance of mu1 hat. Therefore, variance of mu hat which is given by this is lower than variance of mu1 hat. Therefore, mu1 hat is not an MVUE. This is the part A. Now, we will solve part B. Given Tx is complete and sufficient, therefore, any unbiased estimator as a function of Tx will be MVUE. And we know that is mu hat is equal to summation xi I going from 1 to n divided by n, that is equal to Tx by n. So, it is a function of Tx, therefore, and it is unbiased, therefore, it must be MVUE. Therefore, mu hat will be the MVUE. So, we will go to part C now. Apply appropriate theorem to find E of mu1 hat given Tx. Now, according to Rao-Blackwell theorem, this quantity E of mu1 hat given Tx is unbiased, and Lehman-Scheffé theorem says that Lehman-Scheffé theorem states that there is only one unbiased estimator as a function of Tx. Now, this quantity is E of mu1 hat given Tx is unbiased and it is a function of Tx. Therefore, this must be equal to 1 by n summation xi I going from 1 to n. Therefore, E of mu1 hat given Tx must be equal to 1 by n into summation xi I going from 1 to n. So, here we first apply the Rao-Blackwell theorem, which says that this conditional expectation is unbiased. Then we know that since Tx is a complete statistic, therefore, it has only one unbiased estimator as a function of Tx, and we know that 1 by n summation xi I going to 1 to n is a function of Tx, and it is an unbiased estimator. Therefore, this quantity E of mu1 hat given Tx, that conditional expectation must be equal to this estimator itself, summation xi I going from 1 to n divided by n. Thank you.